Carbon nanofibers are multifunctional materials of great technological and industrial importance due to their physical, mechanical, and chemical properties. They have demonstrated great potential for applications in nanocomposites, energy storage, and catalyst support. To date, petroleum-derived polymers, for example, polyacrylonitrile and hydrocarbon gases such as ethylene, have commonly been employed as carbon sources for production of CNFs. However, due to the non-renewable nature of petroleum resources, it is of great importance to find alternative sustainable precursors. Lignin exists in the cell walls of all high-level plants. It is the second most abundant natural polymer on Earth and is an underutilized byproduct of the pulp and paper industry as well as the cellulosic bioethanol industry. The majority of lignin removed from biomass is burnt on site for its energy content. Lignin is an attractive precursor for the production of CNFs, not only because of its abundance and low value, but also because it has a highly aromatic molecular structure that results in a large carbon mass yield after carbonization when compared to other natural polymers. The most frequently investigated method for the production of CNFs from polymeric precursors is electrospinning followed by carbonization. This method is not cost-effective if hindered in a large scale because of the low processing speed. In the modified ice aggregation-induced self-assembly methodology, lignin is first dissolved in water and then sent to a rotary metal drum. Within the drum, continuous films with thickness of no greater than 130 micrometers were produced by delivery of a pressurized aqueous solution at ambient temperature on a rotating metal drum. The drum was tempered by liquid nitrogen to 77 degrees Kelvin. The resultant frozen ribbons of material were subsequently lyophilized to liberate the templated lignin network. The image shown is a rapid freezing device for lignin nanofiber production, depicting a lignin solution contacting the drum, freezing into continuous ribbons, and subsequently being collected in a cold storage vessel. A. Liquid nitrogen is delivered to the drum from a high-pressure tank at 1.4 megapascals to maintain the drum at the desired temperature, which is 77 degrees Kelvin. B. Steel drum is affixed to a variable speed motor, rotating at 300 RPM. C. Needle manifold delivers polymeric solution to the drum for rapid freezing. D. Ribbons of frozen solution containing the templated nanoscale polymer matrix. E. Doctor blade to ensure release of frozen ribbons from the drum. F. Spring tension loaded wiper blade used to regulate the thickness of the liquid nitrogen layer present on the drum surface. To ensure quality, the resultant ribbons possessed a nanoscale polymeric morphology as determined by scanning electron microscopy. SEM images showed a fibrous structure with individual fibers having diameters of 100 nanometers or less and lengths typically greater than 10 micrometers. Fibers are sent to a furnace which runs for several minutes with inert gas that does not contain oxygen. When the fibers are heated, they begin to lose their non-carbon items plus few carbon items in form of various gases. The remaining carbon atoms form tightly carbon crystals that are aligned parallel to the long axis of the fiber. The economic benefit of this technology is optimally utilize the lignin waste. Lignin waste is usually used as a low-grade fuel for production of heat and power. Although production of carbon fibers from lignin has been reported in literature, the low mechanical properties obtained so far have prevented their commercial use in reinforcement and/or composite applications. Carbonaceous nanofibers felts derived from lignin have potential applications that do not rely on mechanical properties, but on large specific surface area. The use of low-cost lignin as a precursor to develop carbonaceous nanofibers felts is anticipated to have a great impact on these applications. The properties of this material include a diameter of 70 to 200 nanometers, a length greater than 150 millimeters, electroconductivity of 10 to negative 3 to 10 to negative 4 ohm per centimeter, tensile strength between 2.35 to 2.9 gigapascal, and surface energy of 133 to 275 meters joule per meter cubed.